We only have Ruben and Yonghun. Thank you. Oh my god. Yeah, okay. So today's aim is to quickly run through angular motion. But Ruben, if you need to go and study for MOM quiz, please feel free to go and do so. I'll record this session. I think today can be a short one because we don't have any physics quiz upcoming lah. So MOM more important. You should go and study that. Yeah. So feel free to drop out if you need to focus on that first. I won't be offended. Thank you for coming already. It's super nice. Yeah. Okay, so up to you. Let me open this window. Otherwise, it's very noisy. Okay. It's okay lah. I mean, still got time, right? Saturday, today only Wednesday. Still got a couple more days to study, so don't worry. But if you need to go, please go and study. You stress on it. Okay. So, okay, maybe I can start this question by asking if you all have any particular questions you all need to run through. I think today's, this week's session is mostly on angular motion, right? Otherwise, we can quickly run through some of the questions that were in the lecture notes that is visible to me. Yonghun and Ruben, do you have any questions? Not really. Oh, no? Okay, awesome. Okay, so we quickly run through it like 2 or 3 questions, and I think we can call it a night, and then Ruben can go and study for his MOM. Is that okay? Okay. Let me quickly send some of the questions into the Telegram group. So I think I don't have a lot of questions. I'm not too sure if this has been gone through in your class because I can't see what has been gone through, but if they are, feel free to let me know and then we'll discuss something else. Okay, so I think this is extracted from your lecture notes. Honestly, I think if you can do this kind of questions, you shouldn't have to worry about any other angular motion in particular. Okay, let me quickly stop this. Go over the image. Okay, go back to here and share my screen. Okay. Summary of magnetic field. Yeah, we can quickly run through that, I think. But since there are a few of us, only 2 of us, 3 of us here, maybe you can let me know what in particular about magnetic field you'd like me to run through. Okay, but we quickly run through this question first, okay? So for angular motion, I think there isn't much to remember. I think the scenarios are mostly analogous to linear motion, right? Linear motion, we have our F is equals to ma. Is equals to ma, then similarly angular motion is just the torque times moment of inertia times angular acceleration. Okay, so we see force torque are the same, mass, instead of mass, angular motion we say moment of inertia, and instead of linear acceleration we say angular acceleration. Okay, and then the other thing to bear in mind is the kinematic equations for rotational motion. Okay, rotational kinetic. So remember our linear one got s equals ut plus half at square, right? Rotational we just theta is equals to ut plus half omega t square. Oh, we have us. Hello, Jin Hao. Thanks for joining our team today. Okay, then etc. for the rest of the things. Of course, it's important to remember that just as how F is equals to ma, the F in F equals to ma stands for the net resultant force, right? Or the force acting on it, the summation of the forces. So too for rotational motion, right? Torque is the summation of torque. It's equals to moment of inertia times angular motion, angular acceleration. Okay, so let's quickly run through this question because I think it's fairly interesting. So it says that the uniform rod of mass m and length L pivot on frictionless hinge as shown, head horizontally and then release. Then at the moment of release, then it asks you to find this stuff lah. Okay, so the first one, what is the angular acceleration of the rod? So remember that our equation, we have tangential acceleration or linear acceleration is equals to the radius multiplied by angular acceleration. Oh damn, what happened? Okay, radius times angular acceleration. Okay, then remember that here our acceleration is caused by, the linear acceleration is caused by gravity, right? So gravity is our linear acceleration. So this distance r represents the distance from the point where the force is acting to the moment about the top, to the point, the pivot, right? The pivot. And this, in this case, is just L over 2. Then we can find our angular acceleration very easily. I think it's 2g over L. Okay? Okay, then for part B, they ask us to find linear acceleration at the tip of the rod. So remember that just use this formula. We know that angular acceleration is equal to 2g over L. From the tip of the rod, the r, our new r, instead of L over 2, it's going to be L, right? R is equal to L at the tip. And therefore, our linear acceleration is going to be L times angular acceleration, which is just 2g over L, and this is going to give us 2g. Okay? So just 2 times that of the linear acceleration in the center. Okay, next one. Next one I think is a bit interesting. So they ask us to find the angular velocity of the rod when it reaches the vertical position, right? When the center of mass is over there. Now I think most of us, when we think of this, we will think of the kinematics equation first, right? Remember, kinematics is S is equals to ut plus half at squared. And similarly, v squared is equals to u squared plus 2as. Then maybe we can look at this and say, hey, you know, that's the linear equivalent. Our rotational equivalent is going to be ws squared, omega s squared. It's equals to initial omega plus 2 angular times the angular displacement. But that is wrong. We can't use it in this case. That's because our angular acceleration is not constant. Remember the kinematics equation that we normally have, we assume constant acceleration. And we look at this, we say that, hey, okay, so our linear acceleration is going to be constant, right? But our angular acceleration, first you put down here, then when it's like that, you still put down like that. Then when it's like that, you still put down like that. So we can see that the angular acceleration is not going to be the same, correct? Because the force is not going to be the same, the torque is not going to be the same. The torque actually decreases as you go down. Torque due to gravity. Okay, so we can't use kinematics equation in this case. So the other thing that we can rely on is our conservation of energy, right? Because you see, initially we have our mass over here. The final mass is going to be over here. So we can say that the change in gravitational potential energy is going to be mgh, right? So it's mg. H is going to be the height difference. In this case is L over 2. And all this change in gravitational potential energy is going to be converted into kinetic energy. And recall that for rotational motion, the kinetic energy is just half moment of inertia I omega squared, angular velocity squared. Okay, this is similar to linear case, so it's half mv squared. Okay, so we can find the change in energy. This is going to result in a change in kinetic energy. We know that at the start, there's going to be no no rotational motion, right? No omega. Then we can find the final omega. And of course, we can also find the moment of inertia. For the case of a rod that's balanced at the end, I think in the formula list is given as 1/3 ml squared, if I'm not mistaken. Okay. So, welcome back, Ruben. So we just solved this part C. So just quick recap. We cannot use kinematic equation because the angular acceleration is not the same. And it actually changes as the rod swings. That's because the torque is not the same. And the torque is not the same because while the gravitational force is the same, the perpendicular distance is not going to be the same. Right? So we cannot use kinematics equation, therefore we must use conservation of energy. And what energy is conserved here? The difference in GPE is going to be your change in kinetic energy. Okay. Then if we know part C, we can find part D very easily. So we call that V is equals to omega R, and then the tip of the rod, our R is just L, right? We found our omega already. We can find V very easily. Okay. Are we good? I think this one should be quite straightforward, I hope. Okay, if that's okay, we can move on to the next question. I think it's also from the notes. Oh, okay, Johan, feel free to ask anything if you need. When do we use Ke for inertia? Okay, we have to use Ke for inertia in this case because we can't use the kinematics equation, right? But then we know that in this case, they tell us that the hinge is frictionless. So as the thing rotates, there's not going to be a loss of energy from the rotation itself. So the only change in energy is just GPE to kinetic energy. So normally for rotational cases, we can like start to think of two possible ways to solve them, right? One is using the kinematics equation, the big four equation, but in rotational form. The second one is in conservation of energy. So we can't use the big four because acceleration is not constant. Does it make sense? Young, what do you mean by you haven't, or like you haven't studied rotational motion?
I sort of haven't started yet because the prof sort of like rushed a lot, so I didn't really understand.
Okay, but covered already lah. Okay. So maybe I quickly run through rotational motion. Is that okay, everyone? Just run through some of the key concepts that I think we all need to know. Okay, then after I run through the key concepts, I will look at the question to that sense. Okay, so the first important thing to note is we know, okay, linear case we have like displacement, velocity, and acceleration, correct? Angular case, I'm pretty sure we all know the analogous or like the similar way to express it is angular displacement theta, angular velocity omega, and angular acceleration alpha. All right, and these are related from this equation. Linear displacement is equals to r theta. Linear velocity is equals to r omega, and linear acceleration is equals to r alpha. Okay. Okay. Then for linear case, Newton's second law tells us that resultant F is equals to ma. For the angular case, it's also going to be very similar, right? Angular case is just going to be the resultant torque is equals to moment of inertia times angular acceleration. So torque is just force times perpendicular distance. Okay, so for example, if we have a hinge like that.
Sorry, is it something like moment, like in MOM?
Yes,
like
correct. Torque is basically a moment actually. So just force times distance. Okay, yeah, correct. So 10 newtons here, let's say this one is 0.5 meters. Then our torque, due to the force at this point, at this pivot, is going to be 5 Newton meters. Yeah, torque and moment is the same thing. Okay, remember that this distance is perpendicular distance. So for example, if I have a beam like just now like that, the case, okay, at the pivot, and this angle, let's say, is 45 degrees. Then from the center here, I have my weight acting downwards, mg, right? The torque that is experienced about the pivot is not going to be mg over 2. Okay, because this has to be the perpendicular distance. So we can find the perpendicular distance either by considering this distance, or we get the component of the weight that's in this direction. Okay. So this moment of inertia term, normally it's given to you for very weird shapes, but for standard shapes, I think you're expected to know. So Jin Hao is right in saying that I can be equals to m over 2, mr squared, but that's the case when you have a point mass. Okay, so if I have, let's say I'm holding a string up, then the string, at the end of the string I got a ball. Then this ball is just m, and rotates around. In this case, yes, the moment of inertia is equals to mr squared, but it's not the case for other objects.
Sorry, for you to, because I remember the probably say about half mr something, or mr.
Yeah, correct. So this moment of inertia is like mass. It really depends on the object. So I think one slide of the lecture notes has a list of okay, give me a moment, let me try to pull it up. So different objects and different shapes can have different moments of inertia. Even if the objects or the shapes have the same mass, right, they can have different moments of inertia depending on how it looks like. Okay. Okay, got it. Let me take a screenshot. So the actual definition of moment of inertia is, the math formula, right? The integral of, mathematically is the integral of r squared dm, correct? But then we hardly ever use this. So if you look at the picture in the telegram, see different shapes can have different moments of inertia. Yeah, and I think it will be shown in the formula list. So mr squared is for point mass. For some other shapes, for example, a beam rotated about the end, it's going to be 1/3 mr square. I think for being rotated by a middle, I think it's another formula. 1 over 12 ml squared. And this is L. So we can see from the middle, right? At the middle, the moment of inertia is actually smaller than the moment of inertia at the end, right? So you can think of it like the mass as I spin in the middle is like smaller than the mass as I spin in the end. And this means that it is actually easier for me to spin a pen like this in the middle than it is to spin about the end. Okay? So like easier to accelerate a heavier object, easier to accelerate a lighter object, easier to rotate an object with smaller moment of inertia. So we just based on the shape and apply. Well, yes, correct. If the shape is given in the formula list. So later we will see, for example, in the case of a pulley we don't know, right? We don't know what is the moment of inertia. So now it looks like a disc, but actually you review one side, it's like that. I don't know how to draw a pulley actually. Like that, for example. Then from that case, right, we will need to use Newton's second law. We need to use this to find the moment of inertia. Okay, so if it's one of the known shapes, like they tell it's a ring or they tell it's a disc or point mass or rod, then yeah, you can just use the moment of inertia formulas from the formula sheet. Otherwise, you need to find from Newton's second law. Okay, nice. There's one question in tutorial. Junhao, can you send? Yeah, please, thank you. Okay, right. So back to this, Anna.
So basically, F equals ma is equivalent to torque equals to I acceleration.
Yes, exactly.
Okay.
Correct. Okay, very good. Yeah, so I think if you can grasp this, right, you can grasp exactly what you said, then you should be able to do this.
These torque are more for like mechanism wise of kind of acceleration. That's it. Like how the beam being turned or like this being turned compared to F equals ma is more
Yeah,
like
correct.
physics.
Something like that. Because if there's any gear or anything, anytime there's rotational motion, right, then we need to use this torque is equals to I alpha law. Yeah, and it so happens that in mechanical engineering there's a lot more rotational stuff. Okay, okay, so maybe we look at the question which Junhao sent first, okay? Okay, let me try to solve it. Once again, no promises, but we do together. Okay, is it question 5 or question 6?
Question 6 is the one that need to use the torque equation.
Okay. this gives us 4.3 times 10 to the power 4. But then the answer is 2.2, right? So it's about half. So this side. And then from the formula sheet, we can find that the moment of inertia for this is mr squared. Yeah, that's a very good question. How come it divide by 2? Let me see. Okay, let me double confirm. Moment of inertia. Oh, sorry. Yeah, it's mr squared over 2. I see. Mr squared is for a ring.
I don't think need to use divide by 2 because I see from the formula sheet, you just put there half mr square.
Yeah. So okay, so the moment of inertia for a disk about its center is half mr squared.
Yes, correct.
Yeah. So if we sub this into the equation, we should get the correct answer, I think. Yeah, I think Jintao, you and I made the same kind of mistake. Like you look at lecture notes, right, and then lecture notes say the prominently mr square, but that's actually for the ring case, the hollow ring. The tin hoop. I got tin hoop. Yes. Thank you, Yonghun. Yeah. Okay. So do we need to do question 5? Okay, we also try to do question 5. Okay.
Yeah, that's question 5.
Okay. Okay. Now let me copy this. Okay, so people 1 of mass 75, the other 25 set number both of mass 78. What in the world is this? Yeah, at first glance I can't see why nose is so bad. We didn't have we think of the people in the boat as masses. does the answer happen to be 2.412 meters? Do you have the answer? Can I check if... Okay, so it's 0.412. Okay, yeah, let's quickly run through this question. So, okay, no worries. Yeah, so let's consider what we need to know from this question. Right? This. Okay, so they tell us the hint is the center of the mass of the whole system with respect to the shell remains unchanged, which is expected because there's not going to be a force, not going to have any resultant, not going to have any change in resultant force as the people switch their positions. So let's assume that they are all point masses, including the boat, right? So we have, let's say that the mass, the fatter guy is at the left. So we have 1 point mass is 85 kg. Oh yeah, no worries. Okay, where was I? Yeah, 1 point mass 85 kg. 1 rowboat mass in the middle, point rowboat mass 78 kg, and all the way at the end, 1 point mass 55 kg. Right? So the distance here is 1.5, distance here is 1.5. Okay, can we find where the center of mass is? We can, right? We said, for example, we set this as the reference frame, this left guy. The center of mass is going to be 78 times 1.5 plus 55 times 3 over the total mass, right? 85 plus 78 plus 55. Okay, so this is going to give us where the center of mass is for the original case. And this should equate to, I think, 1.294, something like that. 1.294 meters. So we say, okay, the original center of mass is going to be somewhere over here. Okay. No, sorry, the other side. It's good. Must be lesser than the halfway mark. Going somewhere over here. Okay. Where this distance here to here is 1.294. Okay, now we consider the case where after they switch the places. So after they switch places, right, we know that, okay, first thing is we know that the CG or the center of mass is not going to change, right? Center of mass should be unchanged, correct? So we know that the center of mass after they switch places is still going to be at this, from our original reference point, 1.294. But when we try to find the center of mass with reference to the new reference frame, the new guy sitting on the left, we are going to see that the boat actually moves a little bit. Okay, so we consider the new case, new case where the guy is to the left. Let's say this is the 55 kg point mass, and then we have 78 kg here, and then once again at the other end is the 85 kg. So they swap places, right? Okay, so can we find what is the center of mass with respect to our new frame, to the new left side guy? So we're trying to find this, right? We can, right? We can find this using the same method that we did. So it's 78 times 1.5 plus 85 this time, 85 times 3. Once again, divide by the total mass. 5 plus 78. Okay? And then we should get this to be equals to, I think just now we got 1.706 meters. So this means that our new center of, our new reference frame from the leftmost guy to this center of mass is going to be 1.706 meters. So originally, from the left reference, the left guy, the original CG was 1.294 away. The CG never changed. Center of gravity or center of mass never changed. But then our new reference frame says that it's 1.706 meters away. So that means that this distance, let me change color, this distance, right, must be 1.706 minus 1.294. So it actually moves towards the left side. Move towards the side where the fatter guy was sitting. Okay, does this make sense?
So we take the center of mass to be the reference point?
No, in this case, I'm taking the left side.
As in for the part 2, like the second part where we're finding the change of position.
This one?
Yes.
My reference point, I always set it as the left side. You can
So
set the
meaning you set the reference point at the place where the 85 kg person was sitting initially.
Yes, correct. 对了。
Okay. Okay, understand.
Okay, nice.
Thank you. There's one more question that I sent.
Okay, can. Yeah, no problem. Yeah,
Yeah.
let's take a look.
Because that question I don't really get the logic also. It's like the painter walks in different direction and they want to know the thing.
Okay. Can you 顺便 send me the answer also? So I know. Okay. Okay. Okay, this is an interesting question. I think they try to trick you with what's the meaning of the word safely. And in this case, it is not safe when the whole thing starts to rotate lah. Okay, starts to have some resultant angular motion, some resultant moment that causes it to rotate. Okay, so that's the meaning of not safe. And if we try to visualize, right, that can happen in one of two ways, right? Either he stands super close to the edge here, the painter stands super close to the edge, and then his weight is larger than all the weights that's opposing it. So the net moment of him standing here is going to cause it to rotate like that, right? And if that net moment is larger than all the other moments that cause it to rotate like that, then we know that this thing will cause him to fly off the edge, right? It will rotate like that. Rotate like that, he'll drop down. Conversely, if he stands on the other side, the same thing can also happen, right? If he stands on the right side, then if his net moment about this direction is larger than all the moments about the opposite direction, then he also can flip and then he'll drop off. Okay, so that's the meaning of unsafe. Now we need to consider what are the cases that will cause him to cause the entire platform to flip. Okay, so the platform we imagine it as just a long beam with two possible supports. To here, right? 1 meter away. We say that this beam is massless, but to account for the weight of the platform, the weight of the scaffold, we say that there's a point force going down 25 kg. There's also a random can of paint, right? The random can of paint going down 4 kg. Correct? Okay, let's consider the case. Oh, welcome back, Yongwen. Let's consider the case where he stands here. Consider the case where he stands here. Okay, so we know that if he stands here, right, and then when it starts to get unsafe, that means that it's starting to already rise up, right? Interesting. Someone accidentally muted me. Yeah, if you find me irritating, feel free to just let me know. No lah, kidding. Yeah. Okay. So I think I was saying just nice when it becomes dangerous, right? It is starting to rotate, right? Starting to become like that. Just nice become like that. And we know that because this is a rope, as we push back against the rope is not going to exert any force, right? The rope is only exerting a force upwards if it's taut. If we just move the platform idea, it's just going to crumple like that. Okay? Okay, so if that's the case, we know that we only need to consider moments about here. Okay, moments about here. And if we consider moments about here, we just say that, okay, we have this guy, let's call it x distance away from the pivot. And then we just do the balancing of the moments. Okay, so we say we got 65 kg, 65 times g, right? Gravitational constant, acting at the distance of x away. That's going to cause it to rotate counterclockwise. Then we consider all the clockwise moments, right? This one we got one can of paint there, so it's 4g times 1 plus the weight of the scaffold, right? So that's 25g times 2, right? Because this is 2 meters. Okay, then we find that we get our x equals to 0.831. So in other words, it's about 17 away from here. Correct? I think that is 5 cm of the right edge and 17 cm. 5 cm and 17 cm of the right edge. Okay, I'm not too sure what that means, but when you get your x, you should get 0.831. So x is 0.831, which means that from here, from the left edge, okay, I think they might have meant left edge. This is going to be 17 cm away. So if he is less than 17 cm away from the right edge, this whole thing is going to rotate in this direction and he's going to drop off. And then he can claim his CPF insurance. Okay, otherwise, we consider the opposite case. We look at if he's standing on the right edge.
Actually, I got it already, I think.
Oh, okay, nice.
Because I think the main problem was like I was looking at the picture description, so I assumed that the man was standing there. So I can't figure out where to find the man, like how to use the man as a point.
Okay, nice. I mean, you understand lah, because they say it's how close can he approach the end.
So now the assumption is it's like just assuming that he's at two different points lah, both the left and the right.
So he can walk freely along the platform, right? Walk anywhere here. You consider the most extreme cases, huh?
Okay, then I think I got this already.
Okay.
Oh yeah,
nice.
for the previous question, right?
Yeah.
I went to see. I don't really understand like if like your reference point is at, for example, at x equal to 0 cm or 0 meter. Then if you use the same reference point, shouldn't the boat move to the right instead of like towards the lighter person rather than the heavier person?
Shouldn't the boat move to the right, towards the lighter person? How come?
No, because if like, okay, you see the graph that you drew. So for example, at the first initial point, right? Your reference point is at the 85 kg.
Okay.
So that's for scenario 1. Then scenario 2, when they swap places, your reference point is still at 85. So shouldn't your x cm from 85 all the way to the right?
No. In the second, okay, my reference point is always the left side of the boat, not where the fat guy or the thin guy is.
Okay.
So if my left side of the boat originally is the 85, so the boat will look something like that, right? You got one very nice boat. It's always here. This is my reference point. Then the second, after they switch case already, right? They switch place, the boat is going to look like that. So the same thing, my reference point is still the left side of the boat. It's not where the people are at.
So case 1 and case 2, there's no difference. As in like, for example, the boat position.
No, the boat position is going to change. The center of mass of the boat and the two people are going to stay the same.
Because I don't really get like why the XM is towards the left and it's not towards the right.
What's your XM? The distance, right? This one, is it?
The XCM, yeah, XCM.
Why is it towards the...
Yeah, because the first scenario is towards the right, then the second scenario is like towards the left.
No, it's not. The second scenario, right? My XCM, okay, so this is my reference point, right? This is my XCM for 1. Then my second case, right? This is my reference point, right? This is my new, this one is my XCM. So it's the same direction.
Also, what I'm saying is like, why are the two reference points not on the same starting line?
Oh, because the boat moved, ma.
Oh. So that's the reason.
Yes, correct.
Okay.
Because I let my starting reference be one side of the boat, one end of the boat.
Oh, okay. Yeah, I'll try to digest this.
Okay.
Okay, thank you.
Yeah, let me know. Okay, and any other things? Otherwise, we can call it early night.
There's only me here, right?
Yes, that's
I think, can you go through with me like magnetic flux?
Okay. Can. Let me pull up some of the notes out, see where we are at.
And like I'm also unsure of like which of the hand rules do I use, because some prof are saying like the right hand rule can use for both cases, then some say you can alternate with your hand.
Okay. Yeah. Let me find the lecture notes. Let me quickly scan through and see what. Okay. Is there any? Okay. So the first question is when to use which hand, right?
Yep. Or which hand like better? Which hand is better? I think.
Depends on the situation. There's no better. There's only right or wrong. So for left hand, Fleming's left hand rule, I think it's if you are given a moving current and a magnetic. Wait. Okay. Let me think of how to.
Dr. Ho said that left hand is for deflected forces, right hand is for intended forces, intended motion, I think.
Say again. Sorry.
Left hand is for deflected motion and right hand is for intended motion. Because left hand is to determine where the force is going, and right hand is the force is already predetermined.
Okay. Right hand, we are talking about the right hand grip, right?
No, Fleming right hand rule.
Oh, Fleming right hand rule. Okay. I am not super familiar about this for now. Can I read up and get back to you next session maybe?
Okay, sure.
Okay. You don't have a test. You don't have physics test soon, right?
No.
Okay. Any more CA until finals?
No more already.
Okay. Hey, sorry, when is your finals, by the way?
Physics
Yeah.
27.
27 November. Wow.
Yeah. On a
Oh,
Saturday.
Oh shit. Okay. Yeah, I'll see if we can get more sessions. Yeah, but yeah lah. I think let me get back to you regarding the left hand and right hand, because I also need to brush up on that.
Yeah, can.
Okay.
Then can we go through magnetic flux?
Magnetic flux. Is your question related to the Gauss's law?
Is it related to Gauss's law?
Yeah, magnetic flux. Magnetic or electric flux?
Magnetic.
Oh man, okay. Once again, because I think it's in the same chapter, I also need to read out.
Oh, okay.
Yeah, I realized I skipped one chapter.
Because I'm quite lost for that chapter.
Oh, okay. Yeah. No worries. Yeah. If you're lost, then probably a lot of people are lost as well. So I will try and prepare something next week now. Is that okay?
Yeah, sure. Can.
Okay. Yeah. I say. I was preparing for angular motion, right? Now that I look at it, I say, yeah, how come I skip one chapter? Oh shit. Oops, my bad. Yeah, okay. Maybe today we just talk about angular motion. Anything else?
I think as of now that's all.
Okay. Okay, can. Yeah, then I will.
Or is there anything that you would like to go through?
No lah. Think. I rely on you all to let me know what I should go through. So because I don't know what are the pain points.
Okay.
Yeah. I didn't take physics. So
Really?
Oh yeah. I come from JC.
Oh, you
So-
took the 101.
No,